Great. Thanks, Christiana, Dolores, for the invitation to speak. Very happy to be here, and a shout out to all those who are staying out early in the morning where you are to watch this. So hope you enjoyed the talk. So I'm going to be talking about the phylogeny and multiple origins of theropod flight, and this picture that you see is kind of encapsulates that transition. You've got some birds up here. These are early fossil birds, a little different from the ones you get today. And then there's things like this that kind of look like a bird, but they're actually not. I'm going to talk a bit more about them. And then you've got other things that that are feathered as well, but clearly weren't flying taxa, have the wrong body proportions and were ground-based. So that's what I'm going to be talking about. So to get us started, I work on feathered dinosaurs and I cover their anatomy. And typically for a paleontologist, that's the bones. So this is a raptor dinosaur with a whole skeleton here. But sometimes, if we're lucky, we can also look at the feathers and soft tissues. And for someone that's particularly interested in the origin of flight, specimens that have those are of particular interest to me. So as well as flight, I'm also interested in the other aspects of the biology of these animals. So that includes how they ate, what they ate, phenomena like molting, how they reproduced, what color they were. So just the general biology of these animals. And what's really important to me is to kind of maintain a phylogeny so that I can basically take all these observations and all this work and look at it in an evolutionary context. In terms of how I go about my work and the team that I have, I'm what you would call a field paleontologist. So I spend quite a lot of time collecting my own material and studying it. But I'm also very interested in developing and applying different techniques and approaches. So for example, I've developed particular imaging techniques that help me to get more information out my fossils. This, for example, is the wing of an early bird, and the yellow around the bones are actually the soft tissues that some laser-based imaging that I use has revealed. I'm very lucky to have some fantastic specimen access, particularly in China, where I'm based. This is me in a museum in Shandong province, where Confucius, the philosopher, is from, and imaging with my laser feathered dinosaurs. And there are actually thousands of these fossils in China. And so if from a scientist's point of view, trying to understand flight development, it's a really amazing data set. And this wouldn't be possible without working with a global team, particularly colleagues from China and places like North America. So just to kind of give us some background. So birds are the only living dinosaurs. So every other dinosaur became extinct at the end of the Cretaceous about 66 million years ago. But the idea that birds are dinosaurs is actually a long-standing hypothesis. In fact, it was actually first proposed in the late 19th century. And you may recognize this particular fossil. It's one of the most famous vertebrate fossils of Archaeopteryx, which we now know is the oldest unequivocal fossil bird. And so this animal preserves beautiful feather impressions, and it basically started a whole branch of vertebrate paleontology involving the development of flight, the origin of birds. So this is a beautiful, famous painting by Hallett, and kind of showing in a picture kind of what kind of happened in general terms. So you started off with ancestors that were ground-based and became feathered, and they used those wings to help them in their life, including in various modes of locomotion, and some managed to break the kind of ground, the limitations of the ground and explore the air. So now you'd be very hard pressed to find a paleontologist that didn't think a bird is a dinosaur. And the hypothesis as we see it today is particularly indebted to fossils from China that were kind of dug up in the last 20 years, including fossils like this. And they also have beautiful feathers like the original Archaeopteryx, but they also have soft tissues. So the kind of very important for studying this kind of transition. Let me just. So talking about three taxon statements, Keith mentioned the challenges in his area with the flies. And by the way, Keith, I really love the kind of tiger shark, not the hammerhead shark fly head. I'm going to ask you about that later. Very, very cool. So this is my three taxon statement challenge, and you have birds and some other guys, and I would say that there's basically no debate about birds being part of the dinosaurs, but there is about what are the closest relatives of birds. And these two groups are what we would traditionally think of as the closest relatives. So one group is called the dromaeosaurids. You probably, sorry. You've probably heard of these before. They're nicknamed the raptors, and they're the ones that they eat people in Jurassic Park, and they're the groups that I actually specialize the most in, my favorite dinosaurs. So there's these guys, and then another group are the troodontids, and you can see superficially they look very similar. I would say that troodontids are a little different ecologically. They have kind of more kind of omnivorous looking teeth and skull plan, and dromaeosaurs are a much more traditional carnivore. One of the kind of classic similarities in this group, you can see very clearly in this reconstruction, it's a very enlarged claw, and you can notice that it's lifted. Some birds today, they do this too. They lift their big claw above the ground so they don't blunt it. And we know this because these are the only dinosaurs at that time that have two-toed prints. So basically, every combination under the sun for this three taxon statement has been proposed, and basically we set out to produce a revised phylogeny ourselves to try and shed light on that. So the thing to kind of appreciate about these particular animals is that there are a few groups that have very long-standing matrices that they maintain, but I would say most people from a very few kind of long-established matrices have kind of done their own exploration and divergences from those. So I guess if you had the genealogy of matrices through time, you would have a few kind of early ones and then lots of new ones now that have been modified in different ways. Our particular one, this is the results that we published late last year. And so we actually have the troodontids being sister to the dromaeosaurids, forming a clade that we call the Deinonychosauria, and that particular clade is the closest to birds. So that is basically our three taxon statement, and it's what we call like the traditional relationships between these animals. So these two form the Deinonychosaurians, and together with the birds, they are the paraavians. So with that phylogeny, we wanted to do different things with it. And one of the things that we wanted to start with was to look at flight capability. So the way we did this is we took our phylogeny and we plotted two particular parameters. And we did this as part of a two-step approach. We first plotted wing loading, which is very simply the body mass estimate of the animal divided by the wing area. And that is a way of telling in modern birds between birds that are powered flyers and ones that aren't powered flyers. And what I mean by that is birds that use their muscle power to fly and ones that don't. And the crucial cutoff between those two groups is being less than 2.5 grams per cubic centimeter. And as you appreciate with fossil taxa, if you have something that's just bone with no soft tissues, it's going to be much harder to reconstruct this accurately. Fossils that have a lot of soft tissues, that have muscle volumes and have entire feathered wings, these values are kind of a bit easier to estimate. Specific lift is the kind of second stage, second parameter, and that is a very specific type of analysis. It's what we call a flapping flight power analysis. So it's basically trying to ascertain for your particular animal, once you've actually pushed off the ground to basically take off, do you have the muscle power capability to then engage your wings and achieve what we call climb out? So to actually get up into the air and be fully airborne. And the cutoff for that is more than 9.8 newtons per gram. And you'll notice the 9.8 is obviously related to gravity there, overcoming that. And this is just, in case you're interested, some of the equations. So basically there's two parts, one that's just between being powered and non-flowered, and the second one, which is a much higher bar to pass, is like, can you actually have the muscle to get up into the air? So really to be considered as having the potential for flapping powered flight, like a modern bird, you need to pass both. So when we put this across the tree, these are the kind of summary results. You'll notice that I've simplified the tree just to kind of make it easier to understand appreciate what's going on. There are two colors you need to be aware of. The first is in orange, and those are basically ancestors or taxa that are very close to having powered flapping flight. They basically lack in some of the calculations. They're just a little bit shy of being able to be powered flyers. So the first thing to appreciate is that down here we have the birds, but up here we have the non-birds, the non-avians. And you can see there's quite a lot of orange here. And that it was a new kind of discovery, because prior to that, people hadn't really appreciated how close non-avian animals were to flying. So that was showing us that the experimentation of the feathered wings of these non-avians was much more extensive than we had known before. Now, getting to the business end, the green are ancestors, and these are obviously taxa here that have powered flight potential, so flapping powered flight potential. And we have up here Rahanavis, which is from Madagascar, the late Cretaceous, and it's part of the Unenlagian. And these guys are also known from parts of South America, and I'll talk a bit more about them. The other non-avian flyer is Microraptor. This is part of a group that you find mainly in Asia and also in North America. And these are in completely different lineages, and the kind of early representatives of Microraptor don't have flight potential, so they're two independent originations. Down here we have the birds, and you'll notice that it's a bit surprising perhaps that you've got a bit of orange there. So the kind of presumption has been for a very long time that the first birds were flyers. It's kind of obvious, but do we really have any kind of reasonable reason why to assume that? In our phylogeny, we have this group Anchiornithines, which in line with some previous authors, we actually place as one of the earliest diverging groups of birds. These had previously been seen as troodontids, And in the particular matrix I use, they actually have always seen them as troodontid. If they are troodontids, then you would expect another origination of powered flight here. But what's been happening lately from my work in my new phylogeny and also some recent work since my work was published is basically agreeing with Anchiornithines as being early birds. So you have at least one origination of flight here. The interesting thing is because some taxa, particularly this Santingia, doesn't actually meet the thresholds, it's actually affecting the avialin ancestor here, and that's why it's in orange. Since this study was published, I've been doing a lot of other work kind of following up on some of the interesting findings that we've had. And we actually, using more granular approaches, using more specimens, we actually find that these guys are poorer flies than we kind of conservatively reconstructed here. So I think my prediction is basically in the years to come that the idea that the first birds were not flyers, I think that's going to get more and more support. If you want to look at this in more detail, the paper was published in the October issue last year of Current Biology. So just briefly about specific trends, I've mentioned the Ununlagians, these African and South American dromaeosaurs. Rahenavis is arguably the earliest diverging Ununlagian, and as a powered flyer, it seems to suggest that these animals may have lost their flight as they evolved. All of these later diverging ones are much bigger, and some are perhaps borderline, like this Bucheraptor here, but these guys are actually massive. One of them was the big one that you saw on my title page is actually Ostroraptor. But there's not many taxon sampled here. There's actually been some new species just described. So there's a lot of work to be done to see, is this kind of a trend of losing flight, and can we actually see more detail here? There's certainly more specimens in which to explore that. So that's one nice lead there. With Microraptorines, Microraptor is like the later diverging taxon in that group. The early ones are very big, have very short arms that would definitely not flighted animals. And we see kind of like a general trend of longer arms, smaller size. And we see at least one smaller Microraptorine that's close to being a powered flyer. Again, there've been some new species described recently. There's definitely a lot more specimens that have still to be studied. So this idea that perhaps there's a trend of improved flight capability along the lineage, that's something that we're actively exploring. So exciting in that area. So this beautiful fossil is of Microraptor. You can see the nice wings on it. It has feathers on its arms, but it also has giant feather surfaces on its legs. And that's been shown by various studies to provide a positive benefit to their flight performance. And this is the critter in all its color glory there. In looking at the birds, I've already talked about this briefly, that the ancestor of all birds probably wasn't a flighted animal, and I think that's going to receive more and more support. But with these animals, with the ones before, there's still a lot more specimens that still need to be studied. So I think we're going to have more data to support this ancestral statement, and kind of more understanding that this early group of birds included some very poor flyers and ones that probably didn't fly at all. So very interesting there. And then going on to a bit of discussion. Obviously, I think everyone likes to think that their phylogeny is the best and the be all and end all. But as I mentioned, there are different matrices in my particular area by certain groups, but also lots of other people who have used those matrices and done their own development work. I've picked out two that are particularly different from my one, that almost represent the other ends of the spectrum. And the reason I've done that is to basically hammer home that no matter what phylogeny you use, the idea that you have multiple origins of flight, that still persists. So Foth et al. 2014, they actually find that birds are the most closely related to troodontids, and that they are then close relatives of dromaeosaurs. So if I take my wing loading specific lift data and I'll put it in that topology, we still get two independent originations in dromaeosaurids, and we get at least one in birds, because Foth, before my study, actually also found anchiornithines to be early birds. So that remains. And if we go to a more recent study published, I think just before my study came out, Motter et al., they described a new Unenlagian, and their topologies is quite different, because they find that dromaeosaurs are the most closely related to a monophyletic clade that includes birds, but two clades that traditionally are actually within dromaeosaurids. And if we plot that out, then we get one origination in dromaeosaurids and at least two, possibly three, within this particular group here. So I think basically with so many specimens still to study and with some new species, I think it's kind of a pretty exciting time to explore, these issues. So the bottom line is that they basically did have multiple flight origins, but the challenge is that given that kind of prevailing and differences between different studies, and as recent as last year, it makes it very, very difficult for us to kind of look at further issues that we're particularly interested in. We're interested in looking at the convergence between the flyers. Did they actually go through the same steps to become flyers? We know where they started from the ancestral data. We can see, how their skeleton structured, and et cetera, et cetera. But because we have so many differences, it's very difficult to say, oh, these guys share these particular similarities in how the flight was assembled, and these ones are different. So that's particularly challenging. Obviously, the solution at the moment is to basically do it for all the phylogenies and compare it. But it's already quite a lot of work just with one phylogeny, so it remains a challenge. So in conclusion, there is some consensus emerging in para-avian phylogeny. For example, with the birds, a lot of people think that anchiornithines are the earliest birds. And there's certain clades where people are agreeing on stuff. But despite some differences, we can still see that the work that I've done in late 2020, proposing that there's multiple origins of powered flapping flight, that seems to persist despite the kind of uncertainty. I also briefly mentioned that although we can say it happened many times, how it happened is a huge question mark. And the way we've kind of been doing it is basically, trying to increase our sample sizes. We have still a lot of specimens still to study. We have some new species that have yet to be coded. Our character list isn't that long. It's maybe like 800 characters, but most of us need to look at the material firsthand, and obviously at the moment it's very difficult to. So I think we basically, in some areas, everyone might have the same data set and you're still arguing, whereas we actually have a lot of data still to add. So I'm very optimistic with how things will pan out. The other thing that's kind of helping this area is work that I haven't mentioned in this talk, we've been using different approaches. So I've mentioned wing loading and specific lift, but there's a whole list of other proxies that you can use to kind of independently and sometimes quasi-independently look at flight potential. And that's certainly helping us to kind of buttress our findings. So with that, I'll open the floor to questions.